A trillion-dollar company just put AI servers in space, and your electricity bill is the reason why.
Wait, are you saying they're literally launching data centers into orbit? So we're covering the merger details, the space infrastructure plan, and what this means for AI access?
By minute 4, you'll know exactly how this impacts your AI costs. Let's get into it.
Welcome to the AI Daily Podcast. Today's news and a deep dive to help you stay ahead in AI.
Today, we're diving into Elon Musk's SpaceX officially acquires Elon Musk's xAI, with plan to build data centers in space.
Stick around to the end for this week's headlines. Let's dive right in.
So let's talk about this absolutely wild development. SpaceX acquiring xAI with plans to build data centers in space. This isn't just another tech merger. We're talking about fundamentally reimagining where we run AI infrastructure by moving it off-planet.
The scale of this is mind-blowing, but I have to ask, is this actually technically feasible? I mean, we struggle enough with cooling data centers here on Earth.
That's exactly the right question. Let's break down what they're proposing. SpaceX has proven they can reliably launch payloads. They did 96 successful launches in 2023 alone. Their Falcon Heavy can carry about 64 metric tons to low Earth orbit. A typical data center rack weighs around 2,000 pounds, so theoretically, you could fit dozens of racks per launch.
But weight is just one constraint. What about power generation? Current data centers consume megawatts of electricity.
This is where it gets interesting. In space, you have access to unfiltered solar radiation 24/7. No atmosphere, no weather, no day-night cycles if you position correctly. The ISS generates about 120 kilowatts from its solar arrays. Scale that up with modern efficiency improvements, and you could theoretically generate megawatts of power with large enough arrays.
Hold on, though. The ISS solar arrays cover about an acre. For AI-scale computing, we're talking massive infrastructure.
You're absolutely right. Let's put this in perspective. OpenAI's GPT-4 training reportedly used about 50 gigawatt hours of electricity. That's roughly what 50,000 homes use in a year. To generate that kind of power continuously in space, you'd need solar arrays covering several square kilometers.
And that's before we even talk about cooling. Space might be cold, but it's also a vacuum. You can't just air cool like we do on Earth.
Exactly. In space, you can only dissipate heat through radiation, which is much less efficient than conduction or convection. The ISS uses massive radiator panels, about 1,500 square meters of them, just to handle the heat from a crew of 7 and basic systems. Now imagine the heat output from thousands of GPUs running AI workloads.
So they'd need revolutionary cooling technology, maybe some kind of advanced heat pipe system or phase change materials.
That's likely part of it. But here's what makes this timing interesting. SpaceX has been developing advanced thermal management for Starship's heat shield. They've gotten really good at managing extreme temperature differentials. And xAI has been working on more efficient AI architectures. Combine those capabilities?
It still seems like a massive leap. What about latency? Even in low Earth orbit, you're adding milliseconds of round-trip time.
For training workloads, latency might not matter as much. But for inference, serving real-time AI responses, every millisecond counts. They'd probably need a hybrid approach, training in space, inference on Earth, with some kind of model synchronization system. Coming up, we'll dig into exactly how they might architect the system, what the economics look like, and why this merger might actually make more sense than it first appears. Let's dive into the technical architecture they'd need to pull this off. Based on SpaceX's existing capabilities and xAI's infrastructure needs, we can make some educated guesses about their approach.
Walk me through what a space-based data center would actually look like.
Picture this: modular computing units, probably based on SpaceX's Cargo Dragon capsule design. Each module might house 50 to 100 high-density GPU racks. You'd have separate power generation modules, massive unfurling solar arrays, probably using next-gen gallium arsenide cells that can hit 40% efficiency compared to the 20% we see in terrestrial panels.
That efficiency gain is huge when launch costs are factored in.
Absolutely. At SpaceX's current launch costs of about $2,700 per kilogram to LEO, every bit of efficiency matters. But here's where it gets really interesting. Starship is targeting $10 per kilogram. At that price point, the economics completely change. Suddenly, launching a megawatt-scale data center becomes financially comparable to building one on Earth.
That's a big if, though. And what about maintenance? You can't just send a technician up when a GPU fails.
That's why modularity is key. Each computing module would need full redundancy and remote management capabilities. When components fail, and they will fail faster due to radiation, you'd swap entire modules. Think of it like Starlink satellites. They're designed to be disposable and replaced regularly.
Speaking of radiation, how do you protect sensitive electronics from cosmic rays and solar events?
You'd need multiple layers of protection. Physical shielding adds weight, so they'd probably rely more on redundancy and error correction. Run computations in triplicate across different modules, use radiation-hardened memory, implement aggressive checkpointing. xAI's Grok model architecture might already be designed with this kind of fault tolerance in mind.
What about the data pipeline? You can't train models if you can't get data up there efficiently.
This is where Starlink becomes crucial. They're already running laser interlinks between satellites at gigabit speeds. You could theoretically create a mesh network where Starlink satellites also serve as data relays to the compute modules. Upload training data during off-peak hours, download model checkpoints continuously.
The power dynamics are fascinating too. No need for backup generators, no grid dependencies, no carbon footprint from fossil fuels.
Let's crunch the numbers. A modern H100 GPU cluster for training large language models might consume 10 megawatts. On Earth, that's about $8 million per year just in electricity costs, assuming 10 cents per kilowatt hour. In space, after the initial investment for power, your marginal cost is essentially zero.
But the initial investment must be astronomical, pun intended.
True, but consider the broader context. Microsoft is spending $50 billion on data centers over the next few years. Google's capital expenditure hit $32 billion in 2023, mostly for infrastructure. If SpaceX AI pulls this off and has megawatt compute capacity for, say, $100 million using Starship, and that capacity operates for 10 years with minimal ongoing costs,
The math might actually work, especially if you factor in the geopolitical advantages of having your AI infrastructure in space beyond any single nation's jurisdiction.
that raises huge regulatory questions, though. Who governs AI systems in space? What happens if there's a malfunction that creates debris?
And security. How do you protect against cyber attacks when your infrastructure is flying overhead?
They'd need end-to-end encryption for all ground-to-space communications, probably using quantum key distribution, which actually works better in space due to less interference. Physical security is, ironically, easier. Good luck getting unauthorized access to a data center in orbit.
What about the competitive landscape? If SpaceX xAI pulls this off, how does anyone else compete?
That's the trillion-dollar question. Blue Origin could theoretically follow suit, but they're years behind in launch capability. Maybe we see partnerships. Amazon using Blue Origin, Google partnering with Rocket Lab or Relativity Space. Or maybe this forces a complete rethink of terrestrial data center efficiency. Stick around. In our final segment, we'll break down exactly what this means for the future of AI infrastructure and give you a framework for thinking about space-based computing. So let's talk about what this actually means for the future of AI and how organizations should think about space-based computing going forward.
Give me the decision framework here. When does it make sense to even consider space-based infrastructure?
Think of it in 3 tiers.
First, workload characteristics. Space-based computing makes sense for batch processing, model training, and workloads that can tolerate latency. Real-time inference, edge computing, anything requiring sub-10 millisecond response times, keep that terrestrial. Second, scale. You need to be operating at hundreds of megawatts before the economics work. Third, time horizon. This is a 10 to 20-year infrastructure play, not a quick fix.
So for most companies, this isn't immediately relevant, but the ripple effects could be huge.
Exactly. Even if you never launch a single server into space, this changes the game. Terrestrial data centers now have to compete with essentially free power and cooling. I predict we'll see massive innovation in Earth-based efficiency, advanced nuclear, deep geothermal, maybe even fusion-powered data centers.
What should platform engineers be watching for as early indicators this is actually happening?
Watch for three things. First, SpaceX filing frequency allocations for high-bandwidth satellite-to-satellite communication. They'll need dedicated spectrum for data transfer. Second, job postings. Look for SpaceX hiring data center architects, cooling system engineers, or XAI recruiting for distributed systems experts with aerospace experience. Third, partnerships with hardware manufacturers. If you see NVIDIA or AMD announcing radiation-hardened AI accelerators, that's a tell.
What about the risks? This could go spectacularly wrong.
The Kessler syndrome risk is real. One collision could create a debris field that makes certain orbits unusable for decades. There's also the monopoly concern. If one company controls both the launch capability and the AI infrastructure, that's unprecedented market power. And let's not forget technical risk. We've never operated computing at this scale in space. Unknown unknowns are guaranteed.
How should the industry prepare for this possible future?
Start thinking in terms of hybrid architectures. Design your systems to be latency-aware and partition-tolerant. If space-based training becomes real, you'll want workloads that can leverage batch processing windows. Also, invest in edge computing. The more compute happens at the edge, the less dependent you are on any centralized infrastructure, space-based or otherwise.
How about the skills gap? The intersection of aerospace and AI expertise is pretty narrow.
That's a massive opportunity for engineers. Start learning about orbital mechanics, radiation effects on electronics, thermodynamics and vacuum. The online courses are already there. MIT has open courseware on satellite engineering. Combine that with your existing cloud and AI knowledge, and you're positioned for a completely new field.
This could also democratize AI in unexpected ways. If power becomes essentially free, the cost of training large models drops dramatically.
That's the optimistic scenario. Imagine open-source projects getting allocated compute time on space infrastructure, similar to how telescope time is allocated to researchers. But the pessimistic scenario is one company controlling the ultimate high ground, literally and figuratively.
So, final thoughts. Is this brilliant or insane?
It's both, and that's what makes it so compelling. Every transformative technology looks insane until it works. The Wright brothers were considered delusional. SpaceX itself was given a 10% chance of success. The technical challenges here are immense, orders of magnitude harder than anything we've discussed, but the potential payoff is proportional to the risk.
If you had to bet, what's your timeline?
First demonstration mission within 3 years, probably a small cluster proving basic feasibility. Production workloads in orbit within 7 years, and within 15 years, if this works, space-based computing could be handling a significant percentage of global AI training workloads. The wild card is Starship. If they hit their launch cost targets, everything accelerates.
For our listeners in platform engineering, the message is clear. Stay informed, think bigger, and prepare for a world where your infrastructure might literally be out of this world.
The convergence of space technology and artificial intelligence isn't just about moving servers into orbit. It's about reimagining the fundamental constraints of computing. Whether this specific venture succeeds or fails, it's pushing us to think beyond terrestrial limitations. And that kind of thinking, that's what drives real innovation. Before we wrap up, let's catch up on this week's infrastructure news. There's a fascinating new development from Amazon that could revolutionize healthcare data analysis. They've just released SageMaker Data Agent, which uses agentic AI to automate the entire data preparation and analysis pipeline for healthcare organizations.
Agentic AI in healthcare. That sounds powerful, but also raises some questions. How autonomous are we talking here?
According to the AWS blog post, it can handle everything from data cleaning to generating insights without constant human oversight. Healthcare providers could potentially analyze patient data patterns in hours instead of weeks.
That efficiency gain is impressive, but I hope they've built in robust safeguards for patient privacy and data accuracy.
Speaking of AI agents, here's an interesting development for developers who want to keep their code local. ZDNet reports on a completely free, open-source alternative to Claude Code that runs entirely on your machine.
Oh, this is using Goose with a Llama and QN3 Coder, right? I love seeing the open source community stepping up like this.
Exactly. The author found it surprisingly capable for local development, though admittedly not quite at Claude's level yet. But the privacy benefits and zero cost make it compelling for many use cases.
And speaking of Claude, there's some fascinating research from Archive comparing LLMs to professional poker players. Turns out our AI friends aren't quite ready for the World Series of Poker.
The paper shows that while LLMs can understand poker rules and basic strategy, they struggle with the game-theoretic reasoning that pros use. Even with agentic tool use, they can't match traditional poker algorithms.
Makes sense. Poker requires reading opponents and managing incomplete information in ways that current LLMs just aren't optimized for.
Now here's a surprising twist. The Verge reports that Claude Code is suddenly everywhere inside Microsoft, with employees being encouraged to use it over GitHub Copilot in some cases.
Wait, Microsoft pushing an Anthropic product internally? That's a bold move, considering their massive investment in OpenAI.
Apparently, even non-developers at Microsoft are finding value in Claude Code. It really shows how the AI assistant landscape is becoming more competitive and specialized.
And Google's not sitting still either. They just released Conductor, an open-source Gemini CLI extension that's getting attention from MarkTech Post.
This one's clever. Conductor uses repository local markdown files as context for AI-driven code generation. It's like giving Gemini a permanent memory about your specific project.
So developers can build up a knowledge base in Markdown that the AI references for more accurate, context-aware code suggestions. That's a smart approach to the context window problem.
That wraps up this week's news. That's our show for today.
If you found this valuable, please subscribe and share with a friend who'd appreciate it.
Drop us a comment with your thoughts on today's topic.
Links to everything we discussed are in the show notes.
Until next time.